Okay, everyone, thanks very much for attending the Balluff Best Practice webinar for the press shop. As mentioned earlier, we've placed everyone on mute, and if you have any questions, please feel free to ask questions through the chat on the webinar software. We'll also open up the muted lines at the end of the webinar and be happy to address any questions that you may have. So with that, let's get started. We're going to focus, as I mentioned, on the press shop for best practice, and we're using the USP phrase, stamp out errors and protect your assets. So our whole goal is to reduce errors in the press shop by using effective sensing techniques, and to protect the assets of our customers' tooling in the press shop, which is horrendously expensive. As most of you know, we're very strong in the auto sector, but today we're going to really focus in press shop environment, which is just not isolated to automotive, but other areas of manufacturing as well. What is a stamping press, or also known as a press punch? It's a machine tool with a ram that moves up and down continuously to cut and shape metal die set. So if you look at the image of the punch press, you can see the ram that would move in a up and down motion. So this is used most often in continuous operation to separate scrap and parts from sheet metal using a die, also known as a tool. Here we have an example of a simple die, and this device perforates holes in a part or blanks out the part using punches in conjunction with the lower mated die, which you see at the bottom. It's also referred to as matrices. So here we have the perforating punch that will move up and down with the arm of the press. We have a stripper that holds the part that's being fed into the press here, and then the part that's perforated or punched will fall out of the lower part of the die seen here. Another form of a die is called a compound die, and that blanks and perforates a part at the same time and the same station. Usually runs with single hit dies. Where you can use this is also with a feeder that feeds the material into the press, as long as the part can be removed in a timely manner. So here we have the part that's being fed in, the punch. Here we're seeing in these two sides the finished part, and the scrap or the slug is going to fall out the bottom part of the matrices. Now, the last point here is important. We need to make sure that this tooling is in an inclined position with an air blow-off aid for part removal. If that does not occur, then the finished part will be struck over and over again, causing severe damage to the tooling. A progressive die is something that most of us have seen in larger press applications, and that's where we typically have a converting of raw coil stock that's being fed into the press with minimal handling. So it's automatically being fed into the press. So here we can see where the stock is being fed into the tooling, and as it moves in this right to left orientation, each station a specific operation of the press will occur to eventually make a finished product here that we see that's exiting the press. What you'll also note here is at every station there's scrap material that's exiting the bottom of the tooling. So it's critical that we have that scrap material exiting the tool, otherwise severe damage can happen to the die. Part of what's in the tooling is a device called a stripper. So stamping dies require some means of stripping or pulling the part from the end of the punch at the withdrawal phase of the perforating process. So here we see our raw material. Here's our punches that come down, The stripper is executing a force on top of the material that's being fed in. So when the perforating process is done and the punch is exiting, it's holding the material in a level position so it's not damaging the finished part. Rolling bolster, this is a device that's holding the front, the top, and the bottom part of the die. And it's a common means of moving tooling in and out of large presses to ensure that it's done in a quick, easy, and safe manner. And typically they're rolled in and out on a rail system. So what we'll be mainly talking about today as far as product is concerned are object detection, or what Balluff refers to object detection sensors. And essentially that's a device that will sense the presence and absence of a target. So that would include inductive, capacitive, magnetic field sensors, photoelectrics, mechanical switches, and ultrasonic devices. So in-die sensing, what does that allow our customer to do? The first point is that it will assist our customer in increasing how many strokes per minute within the press. That will contribute to the customer's overall equipment efficiency to help them become a more productive company. Less die risk. The cost of tooling is horrendously expensive, and to protect those assets is absolutely critical. It's not just the cost of the tooling, but once that press has damaged tooling, then that press will cease to operate, costing enormous amount of secondary costs. And increased airproofing. So all of our customers need to ensure that they're having consistent quality product that they're able to ship to their customer, and to reduce the amount of flaws that are in the finished product that they're producing. So not only do we want to ensure that we're having effective airproofing, but we also want to ensure that we're not having nuisance stops or false calls. We don't want the press to shut down when there's actually not a fault. So it's important that we choose the right sensing device for the right application so the customer is realizing full potential out of their investment. So why should a customer implement an in-die sensor program? The following will be 10 questions that will be useful tips for you to speak to your press shop manager or press shop supervisor. You know, one thing is to identify is what's the cost of die repair when that tooling does get smashed? What's the cost of the overall die crash? The cost of the downtime of the press, keeping in mind that that press is feeding the rest of the company. If the press goes down, then that will begin to starve downward operations of the company, such as welding and assembly. So if those other departments are not able to get parts, then they will shut down. To get caught up, the customer may have to implement overtime and pay those extra costs from within. So what are those costs? A product or tooling is damaged. There may be the risk of producing faulty parts or parts with flaws. So that means that the customer may have to do reworking if it's at all possible, and they may have to do sorting. So those huge steel bins filled with stamped parts will manually have to be sorted through and determine if there are or are not flaws. That's a huge cost. What is the cost of express shipments of finished goods? So if there are faults, that will cause a shortening or a gap in shipping product to the customer, and they may have to arrange for express shipments, which would be an added cost. Firefighting costs. Not all companies can solve their own problems in the press shop. They may have to hire third-party companies, or some corporations may have corporate engineering where they have to send specific people in to help assist and resolve the problems. In any case, all of those involved extra costs that are horrendously expensive. And scheduling alterations. There may be changes in logistics or changes in which shop is manufacturing which product. And lastly, of course, is there lost customer goodwill? Does that problem jeopardize the current status of them with their end customer? So here we have an example of a misfeed with a tooling that was not protected. Product has been fed into the die and struck, and more product has been, or more feeding has been fed into the tooling and struck again over and over until you have the mess that you see in front of you. What's the root cause? That's where we really want to focus, is on the root cause of these problems. So on that particular case, we're looking at a feed detection problem. So 75% of die crashes typically occur at the during the strip feeding process. And out of that 75%, 90% occurs within the first 10% of the feed. So it will become very important in the tooling that we have proper sensors mounted to detect in feed. So what we're saying here is that if inductive sensors are correctly placed in the tooling and they're properly installed, that will go a long way to help resolving this 75% of die crashes. And the other thing that's noteworthy is that if we're picking the right sensor for the right application, that proximity sensor will actually outlast the life of the die. So here we have an example of a cam that was not returned, and it was struck by the die. Here's another example of tooling that's been smashed. This is tooling that's used for an electric motor, for the fabrication of electric motor housing. It's an intricate type of tooling. When this error occurred, this caused that plant to actually cease production until they were able to get new tooling fabricated for them. For example, loop monitoring. That says the coil of steel is feeding into the press. There's roll diameter measurement. So as the coil is converting into the press, we can measure the coil diameter, for example, with ultrasonic sensors with an analog output. Pilot hole monitoring, stripper monitoring, we'll talk about that. Cam return monitoring, buckle lifting, so that's bending of the product, we can detect that. Slug out monitoring, which we talked a little bit about. Short and long feed monitoring. Finger sensing, so on your transfer arms, we can detect with sensors, shovel sensors, the presence and absence of the part that we're moving forward through the press. Pressure monitoring, that's a great application for our pressure sensors for measuring pressure of nitrogen. Shut height monitoring using our linear transducers. Cushion control using our transducers and our pressure sensors. Spring back deflection angle, so using our analog sensing devices. And our inductive couplers would be a good strategy for eliminating the use of multi-pin Harding type connectors, so we can do that wirelessly. Straightener control for alignment of the for the press parallelism setup, and then our networking product. So all of these are areas that we can bring value to the press shop. The steel face inductive proximity sensor should be the workhorse product that you're offering to the press shop. These devices are fully stainless steel. They're impervious to external contaminants such as lube, coolant, chips, and the like. It's fully non-contact. And as mentioned earlier, when it's installed and utilized correctly, these devices will outlast the life of the tooling. They're designed for this environment. We have these installed around the world in automotive environments in the press shop that can withstand high shock and vibration. There's no moving parts. Certainly it's a cost-effective device, and they're easily mounted into the tooling. You're able to mount them flush in metal, and there's both analog and discrete type proximity sensors available. Accessories, it's not just the proximity sensors that you can sell, or the sensing devices. We have a full selection of harsh duty cables. There's stainless steel braided cables, cables that are metal shrouded with PVC coating on it, that are designed for pinch point environments. We have a whole variety of mounting clamps, prox mounts, brackets, cushion mounts, and now we have our new plunger prox. So if we looked at harsh duty cables, the primary cables that you may consider are the stainless steel braid, which is perfect for areas where you may have abrasion on the body of the cord set. There's also our PVC steel armor cable that's crush resistant. For those environments where the tooling gets extremely hot, our fiberglass jacket cable would be a good candidate. That's able to withstand up to 400 degrees Celsius. So let's look at a few feed monitoring applications. Here we have an example of the metal stock being fed into the press, and the lifter has an inductive sensor embedded in it to detect the presence of the metal moving through the press. In this case, we'll have the sensors will all be normally closed. For positioning, we'll be able to precisely detect the blanked or pierced hole over top of the sensor, and it will send that particular output to the press controller. So if the strip is fed either too short or too long, the sensor will not send the appropriate output to the press controller. So here's a closer look at that for examples of short feed, a long feed, and proper alignment. So here, because they're normally closed, this is now on. This won't be sending a signal to the press controller. Same problem here. This is perfect alignment. Here's an example where the proximity sensor is detecting the end of a strip using a 12 millimeter diameter prox. This is our new prox plunger. It's detecting if the strip is missed using the plunger. When it is, it signals the press, and the press stops before the tooling comes in contact with the product. So in this case, we have an 8 millimeter prox that's installed into this device. This plunger when depressed, will trigger the prox, and you're able to, through the set screw, position the prox where you want the trip point to do. There's excellent over travel here to help deal with any over travel concerns. Another common method is using this paddle and prox strategy. The strip comes in contact with the paddle and pushes it into the sensing field. So you can either use that on the end of a strip or off of a French nut. As we mentioned earlier, the proximity sensors are impervious to oil, so in that case it would be an ideal situation. Here we have a proximity sensor that's being used to detect the component loading. The prox is commonly used in this type of application. So here we're looking at the presence of the part before a hit can be made. We talked a little bit about the stripper earlier at the beginning of the webinar. Here's showing examples of positioning of the stripper. This is in proper position. Here we have a foreign object that's been introduced into the work area. The stripper is now on an angle, and not all the sensors are able to correctly read the presence of the stripper. So here we have an example of that, where there's sensors that are strategically located on this block, and we want to make sure that all sensors are made before the product is struck. Here we have an example of a slug, and here we're showing how a bolt head caused a stripper alarm. It caused damage to this device. Now the advantage here is that we've only damaged one particular part rather than contaminating an entire batch. Here's a few examples, of typical foreign objects that have gotten put inside tooling. This can cause massive damage to our customers' tooling and a tremendous amount of downtime. So having sensors correctly placed within the tooling are absolutely vital. So we'll look at some part-out ejection examples using inductive proximity sensors. So in this particular case, we're using a bar-style inductive proximity sensor. Here you can see the part being ejected out of the press, and it's being placed onto this slide. This is a non-conductive material. So as that part slides down this ramp, the sensor is mounted under here, and it will indicate that the part has been correctly ejected out of the press. As mentioned here, placing this device here is an extremely inexpensive insurance policy of ensuring that the part has ejected the press before a second strike occurs. If you have any questions, we'll be more than happy to answer any questions.